We already talked about rotational kinetic energy. For a moment, let's talk about rolling without slipping. Cool. Something to look forward to. On what color is the floor? There's one question about rolling with slipping. You're welcome. I know we haven't done that yet, so I just thought I'd said. Okay. Rolling without slipping. Generally, how do we solve a problem that is rolling without slipping? Just as a simple example, we'll take an object that starts up here and rolls down the hill without slipping. Generally, how do we solve this problem, Mr. P? You're going to use conservation of mechanical energy. What do you need to remember when you're using conservation of energy with a rolling without slipping problem? Tim?
There's rotation.
You have both translational and rotational kinetic energy. Please don't miss that you have both translational and rotational kinetic energy. We've done that. We have now L, angular momentum. Two equations for angular momentum. Loki, give me one or the other. Dorstetter? I omega is the equation for the angular momentum of what, Bill?
Wait, can you say that again?
Sure. I omega is the angular momentum of what? What kind of an object?
Solid. It's a particle.
It's not a particle. I'll accept that. It's what they generally call it an object with shape. But the key there is that it's not a particle, right? We have the equation for the angular momentum of an object that is a particle. What is the equation for angular momentum of an object that is a particle? Bailey?
R cross P.
It is R cross P. Notice that just like torque, you need to be able to use I, J, and K and use the cross product here. And just like torque, I suppose we should identify R cross P is also equal to what, Nick?
RMV sine theta.
I'll put RP sine theta, but yes, RMV sine theta. And the same is true over here. We should probably, oh, we did, good, identified it right there. So we have, this is for point particles. Under what circumstances is angular momentum conserved? Stays. No, it's not whether it has a force applied or not. Angular momentum being conserved. Potterell.
Net torque is equal to 0.
The net torque is equal to 0. How does the net torque equal to 0 mean that angular momentum is conserved? Tim?
Angular acceleration.
Silva?
Because torque is the derivative of momentum, angular momentum with respect to the time versus the
Remember, net torque is also equal to the derivative of the angular momentum as a function of time. If that is equal to 0, that means the angular momentum is not changing, and the sum of the initial angular momentums equals the sum of the final momentums. Which means, whenever you're using conservation of angular momentum, you need to specify what, Emily?
The axis of rotation.
Is often overlooked, that you need to identify your axis of rotation for conservation of angular momentum. The reason is because it is conserved about some sort of point, and that is the net torque about that point is equal to 0. Please remember, when you are talking about translational equilibrium and things like that, you need to draw your free body diagram, and don't forget your reaction force, which is generally, you need to identify in the y direction and the x direction. Please don't forget the reaction force. The big G equation, Newton's universal law of gravitation. Go ahead.
It's equal to negative G m1 m2 over r squared, and it's a vector, so it's like r. With a little thingy on top.
The little thingy on the top is
My
what?
head's spinning.
Oh,
I
you're
just want
welcome.
to say my head is spinning. I don't know how you guys, I don't mean to interrupt because I know your time is short, but I will tell you this, I can't even believe how much you guys can remember. I'm absolutely amazed. You guys will do well, I'm sure, right?
What do you say?
The free
Well,
response part scares me because I've seen some of his free response, but
these aren't my questions. This is an AP test. They'll be done.
they'll probably be easier then.
Yeah.
Take care, thank you.
Welcome. R. Nick. Unit vector. Now, this was a point of confusion for some people on the test that you just took. So please be aware, this unit vector, by definition, always has a length of what, Tyler? 1. By definition, it's a unit vector. That means it has a length of 1. I had several people on the test give all sorts of random answers for that. So please be aware it only has. It's a unit vector. That's what it means.
How well we did on the test.
Kepler's third law. I did not ask you to memorize Kepler's third law. Instead, I asked you to remember how to derive it, because really, in the end, that's the important piece. Sarah Jane, general strategy when solving a problem involving something having to do with Kepler's third law.
You sum the forces in the indirection.
You're summing the forces in the indirection. That is equal to what, Catherine?
Working gravity.
Which is equal to?
G.
True. On the right-hand side of the equation, we have what, Stacey?
Mass times acceleration.
Good, and that's mass times, and we'll put r times omega squared. You could have tangential velocity squared divided by the radius as well. We have omega then. What is the equation for angular velocity? Michael? Loki?
Tangential velocity over the radius.
Ah, true. I agree with that, but we're talking about the definition of angular velocity.
Change in theta over change in time.
Change in theta over change in time. In other words, if the change in time is the period, the change in theta would be 2 pi radians. And you combine those two concepts to solve for whatever you're looking for in this particular problem. Oh, just to make sure we understand, r in your big G equation, big G m1 m2 over r squared, r is not, it is. This is especially confusing because sometimes r is.
Good.
We've done all that. Good. We have the period in terms of the frequency is equal to what, Vlad? 1 over the frequency. So notice the period and the frequency are just inverses of one another. I do want to talk briefly about the gravitational potential energy, which is negative big G m1 m2 over r. One of the things that people always forget about this equation is that it takes 2 objects to have gravitational potential energy. Therefore, you only need 1 equation to describe the gravitational potential energy associated with those 2 objects. Where is the 0 line for this equation, Loki?
Oh, completely far away.
Where r final is equal, I'm sorry, r initial is equal to infinitely far away. Next, we have, with our remaining 3 minutes, the, 2. We have the equation for simple harmonic motion. What is the equation that governs simple harmonic motion, Emily?
The second derivative of position with respect to time equals negative omega squared plus x.
What is omega called, Vlad?
Angular velocity or something else.
Something else. Catherine?
Unit efficiency?
Angular frequency. Angular frequency is often confused with frequency, but it is not equal to frequency. It is equal to 2 pi multiplied by the frequency. You need to be able to remember the 2 equations for the angular frequency of a mass spring system and a pendulum. Yu-Chen.
Which one?
Either one.
Is it roots, Taylor, or M over T?
Which one?
What?
Which one is? Which one is it? Not helpful. Which one?
First one.
Square root of
G over L.
G over L. You need to have those memorized. You also need to be able to derive them. We also have the equations for the periods here. Period equals 2 pi times the square root of m over k, and the period equals 2 pi times the square root of L over G.
Students, it is now time to travel to your 3B class. It is now time to travel to your 3B
Can I please
class.
have 1 minute? We have position as a function of time equals a times the cosine of omega t plus phi. We also have theta times t equals theta max times the cosine of omega t plus phi. Please don't miss, this is theta max. This is for a pendulum. Theta max is going to be the angle.
That's what I did wrong on the test.
I was like, wait, where's this equation? We need this equation.
The energy total of a mass spring system class is what? 1/2 k a squared. It is also equal to 1/2 mass times velocity maximum squared. Thank you very much.